So, if everything has gone well, this program here is going to map this list with this function, correctly type checking it as well, creating a list of ints that is the square of all of these. It's just that easy. It is just that easy. Hello everyone. This is the programming language that we've been working on for the last 2 episodes. And since the last episode, I've gone and implemented a bunch of operators and booleans, just because it's a lot of pattern matching, copy paste, not that interesting. So now the language supports rot, which is rotate. So that basically takes the 3 elements on top of the stack and sort of rotates the bottom one on top. So this one, if we didn't have the rot, it would print 3, 2, 1, but it puts the 1 on top, so it will print 1, 3, 2. I've implemented over, which basically just copies the element below the top of the stack, so that will take the 1 and push a 1 on top, so this will print 1, 2, 1. And I implemented pop, which is just popping off the stack. A lot of languages call this drop, but to me, you pop a stack. So I'm going to decide that in do, the keyword is pop. And I realized, looking over the last 2 episodes that I've done, I never actually explained what the keyword do will do. So we're going to try and implement it today, along with functions and a couple other higher order functions, hopefully. So let me start a new file. So let's call this one functions do. So as a reminder, this is a functional stack-based programming language. So what that means is if I have a list, 1, 2, 3, 4, 5, and I can push a function onto the stack. So that pushes a list of 1, 2, 3, 4, 5 onto the stack as a single element. And then I can push a function onto the stack as a single element. So dup star, as we remember, is basically squaring a number, because you duplicate the number and then you multiply those 2 together. But this is quoted, this is what's called a quoted function. And so this doesn't actually get applied to what's on the stack. If you didn't have the round brackets, what this program is going to do is duplicate that list and then try and multiply the list, which currently will just be a compiler or a diagnostic, an error. But maybe in the future that would make sense to be like a cross product. Like I can imagine this would be a really nice language to do things like matrix operations. Being able to maybe multiply a list by another list, doing a dot product, and giving you like a 2D array or a 2D list, something like that. That's down the line. But if you did that, that would fail. But if you do this, this doesn't compile yet, but this would push the function onto the stack, and then you could do something like this, where map is a higher order function that takes a function as an argument and a list and applies that function to every element in the list. So this would square everything in the list. And then you could do something like this, which would then just print each of those elements. So you can print lists in do. So you could do this, and that would print it as a list. But if you did it like this, that would print each element separately. Now, finally, to reveal what do does. Do is just call a function. That is it. So if I had 5 dup star, in order to sort of apply this function to a single element, that's just do. And I haven't even added do as a keyword. So let's just do that. Let's go to settings, where is it? It'll be like file, file types. That's it. And I have a do, and then we can just add do. And now it gets syntax highlighted. So do takes a function, any arbitrary function. It can take in anything, and it can output anything, and then it will consume as many arguments as it needs, and then it will output the outputs. None of this compiles yet. In fact, now is a good time to show you. I've also I spent some time figuring out how to kind of make the diagnostics pretty. So if I clear this, I was playing around with adding floats. It got a bit complicated because my type checker, all of the arithmetic operations expect integers, and in order to get it to do floats and integers, it kind of became a bit of a combinatorial nightmare. So I think I need more sophisticated types before I can start adding different numerical types. So we're going to leave that for now. We're only going to have integers. So if I try to interpret functions. Oh, look at this. So yeah, so first of all, we don't even tokenize parentheses because we haven't needed them this far. So that's an unexpected character. It doesn't know the keyword map, and it doesn't know the keyword for each, and it doesn't know the keyword do. So let's implement that. Why don't we? Let's start with a really simple example that we can work towards first. So we're just going to go for this. So if I clear up, let me also show you. So booleans. Oh, come on. Booleans. So you have true and false that you can push onto the stack just as literals. You can do comparisons. So you got to remember that things get popped off top to bottom. So push 5, push 10, pop 10. That becomes your left-hand side, greater than 5. And then it gets negated. So the exclamation mark negates. So this would print false. In fact, let's verify this. So what do we expect? We expect true, false, false. Then we have equals, and then so this isn't actually a single token. This is 2 tokens. So 9, 10 equals negated. So this will print true. 5 dupe star is 25. 25 greater than or equals. So this is a single token. It should print true. True equals true is true. 4 equals true. So this will type check and tell me I can't compare. Well, it will say, oh, I expected this, but I got this. Yeah, I expected a bool, but I got an int. And I'm not sure whether it should report the error on the equals, because that's the operator that expected the bool, or on the operation that put the wrong type on. And I think I should do both, but currently I can only print one location. So I need to improve the diagnostic printing, because right now it's quite a lot of spaghetti, and also it only works on Windows, unfortunately. But just for getting a good error out of something I've written, it will suffice. So if I go back into bools and I just get rid of that line, and I do it again, we should see true, false, false, true, true, true. And there we go. So we have bools. Okay, so how do we implement this? So it's very similar to lists, but instead of the only operations being allowed being push operations, where a push operation is just something that takes in nothing and returns a single value. So actually, I could get rid of this, and I could print this list. So let's go back and do functions, so we can print the list. So it doesn't really care what is inside the list as long as it's all the same type and it's all push operations. So you couldn't do true, false, equals as a single element. I might want to allow this at some point, but for now it's easier if it's just literal push operations. So we can do this, and then we can say print that. I haven't actually tested this, so this could explode, but let's see. Ooh, okay. Only push operations allowed in lists. Where are you? Oh, would that be in the parser? So I haven't implemented that. Okay. I thought this was done at the type checker, but it's done in the parser. And as you can see, I then have to like implement this. Ooh. Is it listless or is it? Ah, see. Yeah. So you can't have lists of lists yet. We will need that at some point. But for now, that's not what we're focusing on. We want functions. Entered unreachable code. Oh. Yep. Okay. So yeah, this should be handled a little bit more generically. Need to rebuild. But for now, yeah. For now, that's good enough. Especially so we want to also be able to do something like 3 greater than filter, or rather map and print. So that would print false, 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 true, true. You know, and then you can do filters, which would then return you a smaller list of everything that is greater than 3. For now, we just want dupe star map. So this is what we're trying to compile. So we need new tokens. So let's go to our Lexa, close that so we can see what we're doing. And we want open parenthesis and close parenthesis. I don't really need this structure. There we go. And then parsing that is very simple. If you're interested in how I lexed the double, like the greater than equals or less than equals, I just have this kind of scuffed function that takes in an extra character and says, okay, if you see this character, do this one, otherwise this. It's kind of a scuffed function, and I'm pretty sure that these are the only two that need double wide tokens, or double character tokens, because equals, like in most languages, equals is double equals, because the equals character is used for assignment. But there are no variables in do. There might be at some point, and it might end up looking like how it did in Porth, where you just kind of bind a name to a stack value. So you would do something like 10, and then you would what was the Porth? It would be like let x in end, and so end would match with in, and then within this, every time you said x, it would push 10 onto the stack, and you could do that many times, and it would consume the 10 from the stack. And then within the block, every time you say x, it pushes 10, and then once you leave the block, it's consumed the 10. So you can have variables like that. I don't know if that's how we're going to do it in do, but that'll be later on. Currently, we don't need variables. So let's add our new parentheses. Where did I put them? Okay, but after percent. I like to keep them in the same order. So percent is here. Yep, cool, easy. And that's it for lexing. So then parsing. Parsing is interesting. So parsing is going to be similar to parsing a list. And in fact, it's actually got the same signature. So this is going to be push function. And it's going to be a vector of ops. But it doesn't have to just be push operations. It's a complete just sequence of operations. And actually, it's going to be interesting to type check this. I mean, it's going to be interesting to type check the functions in the first place because we need to do inference, because we need to infer what the signature of this function is. And I actually don't know how I'm going to do that yet. I'm going to figure that out as we go. But you could have something like this, and then you've kind of quoted that, and then you could sort of do. Yeah, so you can have like nested functions. Yeah. I don't really know when that would be useful. I guess as you get into like more complicated constructs, like I don't even know how we're going to do like conditionals or how we're even going to do conditionals in this language. But you need to take like bodies. Like this is kind of like a body in a normal programming language. That you could have if condition, you know, then else. Yeah. So these are like quoted programs or quoted functions, kind of. I guess they're like blocks. These are blocks. Maybe I should call it a block. Yeah, because like when we get to defining functions, like I'm thinking a function might be like fun, foo, and then the signature could be like, oh, int, an int, so takes an int, returns an int, and then inside round brackets you could do the body, because it will use the same syntax. Again, getting very ahead of ourselves. So maybe I'll call it a block rather than a push function. I'll call it a push block. Okay, so this is the code that parses a list. And it's kind of bad. But it's only bad because we have to be so specific about what can go into a list. So let's say token kind open parenthesis. Okay. And we want ops. I don't really like that it's a infinite loop that we have to break out of. Yeah, hang on. Because yeah, we need to recursively parse ops. So that's how we're going to get like lists inside functions and other functions inside functions and stuff like that. And so we needed to say, okay, while yeah, that and yeah, and that. So that's probably complaining because we aren't returning. Yeah, okay. So that actually works. Let's move this aside because we've got such a wide... In fact, does this... Yeah, okay, now that works better. So yeah, if we do this, we want to parse the op and then just add that to ops. So ops push self-parse op. And then if we break out of here, there are two reasons why we broke out. Either we've hit the end of the tokens, in which case we're looking at something like this, where we hit the end of the file and we didn't see any closing parenthesis, so that's an error. So how do we denote that? If self cursor equals that, and let's just do greater than equals just because I'm paranoid. Then we need to report a diagnostic, or report an error. So I said this before, but like a difference between a diagnostic and an error is an error is a diagnostic, but a diagnostic isn't always an error. A diagnostic could be a warning. We don't have warnings, but it could be a warning. So what did I say for this? List missing closing. Yeah. So well, let's just yoink that and say block missing closing parenthesis. Okay. So then we just want to... So we know we got a close parenthesis, so we can just increment the cursor. So skip closing paren. Although actually no, we don't want to skip it because we need it for the span. So we need to say if let token kind no, let close paren equal self tokens self cursor. Don't know what it's after there. And then that, and then we can't move. What about now? Cool. So we have that, and then we just say sum op, and it is op kind push block, and we have our ops from up here, and the span is from 2. So what do we call the original token? Token. Beautiful. So from 2, token span to close paren span. And then I think we need to do the same thing. Yeah. If we get a stray close parenthesis, then it's just unexpected, and then we'll move that up near here. Okay. So that should be it, but it's still not happy. Cannot borrow self. Who's borrowing you? Immutable borrow later. Okay, easy fix. Easy fix. We just get it out before we do any of that. And let's see, does this fix it if I say token span? Nope. Immutable borrow occurs here. Can I just say fuck you? I can. So do I still need to do this? No. Okay. And that's fine because it's just cloning a token, and all a token is an enum and 2 numbers. And yeah, we don't store anything crazy. Like this is the only thing that has anything big, but I'm pretty sure that's just a pointer. Pretty sure that's just a pointer. Okay, so we have a block. So it's say op kind push block ops to do, and then interpreter we will also give that a to do. Okay, so that compiles. So if we, first of all, it's going to complain because map doesn't exist. So let's just do this for now, and it should say that we aren't. We haven't implemented this yet. Okay. Interesting. So our while didn't work. So while this is less than len, and current cursor kind does not equal close parenthesis. Hey, this is what happens when you trust Copilot. There we go. So yeah, we aren't type checking push blocks, and if I forget to close my function, block missing closing close param. Be nice if it showed the whole thing. Be nice if this span was a span from to token span to ops last or else token span, because if it's just a stray errand open, there's no ops to get a span from, so we want to use the same one. This doesn't seem to like it. There's option op. Why doesn't or else return, like, how do you just say, like, oh, if this is none, then return this? Is it just or? No, that still returns an option. Okay, or unwrap or. Expected OP. OP's last map. So we have an OP, but we want its span, and then we unwrap that, or else we just return the token span. Okay. There we go. That's nicer. So that works because we just look at the last op we put in, which was the star, and then span from to just computes the span across those two. So if I forgot to put anything in here, block missing closing. There we go. Absolutely beautiful. So now we need to, well, first of all, we need to fix this. Now we need to type check this. So this is where I actually don't know what to do. Well, I have a vague idea. I haven't actually, like, checked to see if this is the correct way to do this, or if it's even going to work. But the way that I'm imagining this is going to work, and so like I said before, I'm pretty sure languages like this already exist, and they probably do a much better job at it than I'm going to be able to do. But that's not the point of this project. The point of this project is to have fun, which I am, and I hope you are too, and to learn, and to just kind of like flex my programming brain muscles to just kind of, yeah, just try and learn and try and keep my problem solving skills sharp. So I want to try out this approach, and if it doesn't work, then I'll have to think of something else. If it does, then great. So the way I'm thinking of this working, so the problem we have is, like, as you're type checking, it's very easy to type check a sequence of operations, because you have to keep a type stack. In fact, I can show you. So the type checker struct, it has a type stack, which is a vector of types. And since the last episode, I've changed it to be a stack of types and a span of where they were defined, so that you can report. So this is what I was saying is it clearer to report the OP span or the type span? So every time we match on the in or on the input, we get the span that input was defined, and we can say, you know, this type was defined here, but we expected a boolean here, but there's an int here. So the way that we type check is very simple. an operation will say, oh, I take in an int and I return 2 booleans, for example. And then we say, okay, you take in an int. So for every type in your ins, we just check that type stack to see is what's on top of this type stack compatible with that. So either it is exactly an int, or we have generics, and then it will erase that generic to be an int, for example. So that's really easy when you have that type stack. But when you go into a block, you have to start with a blank type stack, because this shouldn't affect anything outside of its scope. And it has special rules, because if you was to just have this program free floating in a do program, this wouldn't compile because there's nothing for dupe to dupe. But inside a block, that's fine, because now this block, like we can see that this block should take in an integer and it returns an integer. But we need to compute that, and we need to compute it generally for any function. So what I'm thinking is we have a different strategy for blocks, where we compute the signature of each of its operations. It has a type stack of its own, but if we reach the bottom of that type stack, or rather if we encounter something that doesn't compile, or we have something wrong, I guess it's just the bottom. So let's start with that case. So in this case, we dupe. Dupe expects a generic, but there's nothing on the stack. So we push a generic into our ins. And then we see star, which expects... so dupe will push a generic into the ins, and it will push 2 of that generic to its outs. And then star will see those 2 generics, and it will say, okay, that has to be 2 integers. It will erase those 2 ints to be... erase those 2 generics to be integers, and it will then obviously erase the input to be an integer, and it will consume those 2 out integers and say, I will output an integer. And so what you end up with after you've done that process is you have a list of ins of a single integer, and a list of outs, which is also a single integer, which is the signature of this block. So that's how I imagine this is going to work. But whether that's actually going to work or not, I don't know. So I'm going to make a quick break and plan out how I'm going to implement this. Okay, so I've started to... So we're in get signature, because I think that's where we need to do this type checking. So we're trying to get the signature of this function. So we have ops. So we need to create a ins array and an outs array. And then we just basically say for op in ops. Yeah. So we want to get the signature of this op. So we'll call this op ins and op outs. And this is going to annoy me, so we're just going to slap a do there. And then we basically just need to do what I said. So for op in op ins, we need to match ins pop. Yeah. We need to match the ins pop. If we have some type kind, then we just expect type. So the expected is that type kind. The actual is the op in. and the span, I believe, is the last argument. Yeah, is the op. It's the span of the op. If there's nothing, so this is where we would normally throw an exception and say, oh, well, not throw an exception, but, report a diagnostic and say, hey, we expected there to be this, but there was nothing in the type stack. But this time, and in fact, it's already predicted this. Yeah, we push the in into the op. We push the op in into the ins. Yeah. We might also need to check the outs, I realise. Okay, we'll get there. I'm starting to see the cracks in this approach. But let's keep going for now. So for op out, in, op outs, I think then we just straight up just push outs, push, op out. Yeah. This might work. This might work. So let's test this. So let's print what our ins are. Oops. What our ins are and what our outs are. And we'll say ins, outs. And then we'll to do. So this should type check this and then stop. Yeah, see? That's not quite right. So it correctly says that it expects an int in. But yes, it is now saying it's outputting 3 values, which isn't right. So I think it actually needs to first match outs pop some out. And then if there's none, we do this. So what have you done here? Outs push out. If there's some out. So okay, we're the star. The outs are currently 2 generics. So you want to pop that. We just want to pop that. No, we want to self-expect. Yes. We want to do something like that. Where, okay, there's something on the out. Does that match what I need in? If so, consume it. Otherwise, error. If there's nothing in the outs, then we check the ins. And then if there's nothing in the ins, we say, okay, well then that's a requirement for my function. So this then becomes this. Yeah. So what happens when we run? Op-outs doesn't live long enough. Ooh. Hold on. Okay, that's where you've gotten confused there. You should be a vec of type kind. Because yeah, every time I mess up what type is getting put into the array, it's so you should be that. Okay, do I still need to clone this then? Nope. Okay, we're back. Great. It's close. It's closer. So this is now the correct number, but it's not the right type. Okay. So we get the signature. So the signature of dupe is generic, generic, out to the same generic. Oh, sorry, other way around. Generic to two of those generic. So op-ins is a single generic, and we have nothing in ins and outs. So outs pop is none, ins pop is none, ins push op-in. Because we don't erase generics here. We don't erase any generics here. Okay, so we've pushed a generic into the ins, and we've pushed two generics into the outs. How do I erase generics elsewhere? Because it would be nice if I only do it in a single place. Here. Yeah. So we need to match, if it's sum, get a type kind, and match the array. Ooh, okay. Yeah. So do we need to match this and see if it's a generic? And if it is, erase it. Otherwise, check the erasure. Because that's kind of annoying that we have to do that in two places. So let me just yoink this. Because this seems to be the simpler case in the outs. Yeah. So what are we doing? Where did we get that from? So matching the output. So for output in outs, op out and out. So we want to match op out. And then if it's a generic, we do that. Otherwise, we do that. And we're not pushing to the self-type stack, we're pushing to outs, which means we aren't actually... Okay, so the ins and the outs, they don't have any span information. So now we should be correctly erasing outputs, but that wasn't the problem we were having. So this should print the exact same thing. Yeah. So the problem is we aren't erasing ins, which is fine, because we can do this. So when we are matching the inputs, we match on the self-type stack pop, so we're matching on the outs. So if it's some generic index, and I to do it, does it to do me there? It does. So here we want to erase the generic. Okay. Oh, it's quite hot here. It is it's the 12th of July, and it's like, God, I don't even know. I don't know how to see it on the computer. Check my phone. It is 28 degrees Celsius, which is some number in Fahrenheit. But as you can tell, I am English. We do not have air conditioning here, so I am just sitting in that 28 degrees raw. So my brain is struggling with this. But we're almost there, right? This feels like this should work. So we have a generic in the outs, which is our generic. So let me duplicate this and okay. No. Let's just get back to where we were. Okay. So we have a generic 0 in our ins, which is this. So we want to how do we do it? We match self erasures get index. Some erased or none. So either this generic has already been erased, in which case we figure it out, or it's this. And we don't push to the self-type stack, we push to the ins. And we don't need the span, we just want the erased. Do we need to clone it? Yes. Okay, whatever. It's just a type. So now if we do that, it's worse. Okay, it's worse. Why is it worse? So we have a generic. We match on that. If it is not erased, we need to erase it. Okay, what am I doing? So if it's none, what do we do in the none case up here? Self-erasures insert. Yeah, that's what we do in the none case. We do the erasure, and we don't. Did I take too many things? Yes, I did. So push op in. That doesn't seem right, does it? What type kind will we be pushing in there? In the input. I feel like we're just going to erase the generic with itself. Yeah, and we've still fucked up the number of ins. I'm going to take a break and refill this water because it's going down fast, it's too hot, and I'm going to think about this off camera and come back with hopefully a solution. Alright, I have a solution and I'm not happy with it, but I think it will work. So I think the problem was it was erasing the generics, but it was only erasing them past a certain point, and then like any generics that were still below on the stack just hadn't got erased. So I've just added this these two blocks at the end that basically just, once you've gathered all your ins and your outs, it just goes through and erases what it can. So if I build and run this, it correctly says ins and outs. So if I put a 5 here, is it going to say there's two? Yeah, so there's two ints on the out, and if I put a pop on the end, there's no outs. Cool, cool. And if I just do dupe, yeah, it's just generics. Okay, this seems like it works. I'm sure we'll, as we go and make more complicated programs in this language, we'll encounter where this falls apart. And also, it's just disgusting code. Like, I am not going to be able to understand any of this. Like, I feel like I keep doing this pattern of matching a type. Is it a generic? Yes. Do I have it erased? Yes. Replace it with the erasure? No. Erase it. Otherwise, do something else. I don't know. But anyway, so we have our ins and outs. So it's the temptation is to just say, okay, ins, outs as our return. Block ins, block outs. Let's call this, actually, this isn't quite right. This is erased ins and erased outs. There we go. So we don't need this anymore. So it's tempting to do this, but that's not right. And I'll show you why. So if we save this and run it. Yeah. So it thinks that this whole function is an operator that takes in an int and returns an int. So it sees this operator and it says, well, I expected an int, but I got an array of int. And then at the end, it puts an int on the stack, and then the type checker is saying, well, hey, you need to have an empty stack at the end. But that's not right, is it? Because this is actually pushing something very interesting. This is pushing a function of ins to outs. So we need a new type. So if we scroll past all that disgusting code, and we go here, so we have a block, which has a vec of type kind ins, and and a vec of type kind out. And I think it warrants giving these names, just because otherwise it's not very clear what they are. And so something isn't happy. Oh, this. So how do we display this? It's very interesting. So if we have a type kind of block with ins and outs, we want to write something like fn of something to something. And I'm thinking this is the sort of the syntax for a list of types. So when you declare a function, you need to have a list of types. So I'm thinking something like this. This. Yeah. So what do we need to do? We need to take the ins. We need to map it a map, L to string, collect join with spaces, and then same for the outs. Oh my god. Good lord. Outs. Okay. Let's see what that looks like. Didn't work, because I never actually returned that type, did I? So this instead is, it takes nothing in, so a function pushed onto the stack never takes anything in. And it returns a single type, which is of type kind block. Ins are the erased ins, and outs are the erased outs. Ooh, there we go. So now, of course, yes. So yeah, it complains because we have a list of int on the stack at the end, and then it complains because we have a function of int to int on the stack at the end. Okay, so we type check this. Now we need to interpret it, because we can make this compile if we just say pop pop at the end. I did need to rebuild. So it compiles, but it doesn't know how to interpret a block, which is fine, because I think this is really easy. Oh, it's gonna explode some of the implementations, but we have block, which has a vec of ops. You can't clone ops. Oh, you can't clone vecs. So what does that break? Push a clone. Is it just because op? Yeah, okay. And then op kind, which is fine. Okay. Ooh, for a moment there I was like, oh, you can't clone a vec, and I was like, of course you can clone a vec. Okay. So displaying a value. Ooh, what happens if you print a function? I guess if you try and print a block, it will just say fun. Yeah. Because, like, it doesn't really make sense, and we don't have the type here. So we can't say, oh, this is a function of int to int. It's just a fun. I think that's fine. Cool. Actually, no, these all have default cases. So yeah, if you try and multiply a function, you're going to get unreachable. I mean, the type checker should stop you before then. So if we're pushing a block, that's just self stack push this. Field 0 is never read. We'll get to you. We'll bloody get to you. And it compiles and it interprets. It pushes a list, it pushes a function, it pops them both off without doing anything with them, and it works. Okay, so let's implement map. Let's implement map, and then we can print the output because we can print a list. So this is going to be eager. I could make it that it's lazy, but I think it's more convenient for now if do is eager. So for those who don't know, the difference is whether the computing of the mapping is done at the point of the mapping. So if it's eager, when I say map, it will perform this operation 5 times, regardless of whether I do anything with it or not. So if I do this, it's going to call dupe star 5 times. If it's lazy, what map will do is it will just do something like replacing each element of the list with a function that does the squaring of the thing. So it will replace each of these with like 1 dupe star and then 2 dupe star, something like that, which basically means that it hasn't actually performed the squaring yet. And it's only when you do print and you need to compute the values that it does the multiplying. And so if you do things lazily, it means you can have infinite lists. Because if I had something like, rather than dupe star, I had print for each, and this was an infinite list, it would hang forever before ever outputting anything, because it has to go through every single element of the list and print it. But actually, that's a bad example. Sorry. If it was an infinite list and I was doing this first, it would never print anything because it needs to multiply, or it needs to square every element before it can move on to the next operation. But if it's lazy, it will hit the for each, calculate the first element, square it, print it, and then the next one. You can have an infinite list. So you could do something like a prime number calculator, and you just give it the infinite list of all of the integers and you pass it to the algorithm that works out whether something is prime or not, and filters out the ones that aren't prime, and then you get the infinite series of prime numbers. But that's hard, and I don't want to do it. So we are going to eagerly evaluate. Maybe that's a bad idea, but we can change it later. So let's actually save what we've done so far. So let's do a little cargo fumt, do a cargo clippy, and this is going to complain because there's a couple unused things. Redundant pattern matching. If yep. Else if is none. Change this to erased. Sure, you're the boss. Field 0 is never used. It will be. You wait. Okay. So yeah, that's the only thing that we are missing. Oh, sorry, that's the only thing we're like non-compliant with. but I think that's fine. So let's add all of this and I can't type, it's too hot. Add block literals and type check them, or and infer their type. Okay. Let's add a new keyword. I'm going to put the higher order functions after all of these. So we're going to have the map keyword. Let's close this so we can see what we're doing. And let's go to where we lex the keywords. Here we are. And so you can see this is how true and false are implemented. They just map to a bool literal of true and false. So if we map, we get a map keyword. And then we parse it. And so the op kind, well, it is just a map. So when we match on the token kind, we go to the bottom, token kind map keyword is, just yoink this, map. Now, this is going to be interesting. We now have to type check map, and map needs functions. So map, it needs two generics, A and B. Okay. And the first thing it needs in is a function. So if we open this up and let's just give it hello, there we go. Give it empty for now. So this is just saying map consumes nothing and returns nothing. We need it to consume a block. And it needs to have in an A. And it needs to have out a B. Right? So this is the map. Expected type kind found use size. Yes, okay, yeah. Type kind generic A and type kind generic B. So the types have to be different. In our other case here, like I say, like it's in is an int, out is a bool. In fact, let me just test that quickly. So if I add the remaining pattern for map, I'll just say to do, I build, and I run this, it's probably going to complain. Insertion index is 3. Okay, well that's... Yeah, okay, we need to sort that out. Interesting. So let's go back to this. We'll deal with that in a second. So if we have this, we have a function of int to int. If instead this was saying 5 greater, block is missing closing. Ooh, yeah, okay, that's probably to do with our double. There you go. Yeah, there's an issue with the lexing, I guess, for the double wide stuff. It needs to backpedal if it doesn't get what it's looking for. So you can see that it has a function of int to bool here. So let's just fix that quickly. Go to lexer, and we lex multi-car token if match if it's sum, if not match. Okay. Yeah. So this self cursor minus equal 1, back pedal. Okay. There we go. Yeah, so this is a function of that to that, but something seems to be the matter when you type check map like that. Because it seems to have a higher index than we actually have in the erasures. Is that because when we create the erasures, where is that function? Create generic. Yeah. So we need to say something like self erasures push that. Wait, is that true? Because we always expect it to be erased. Yeah, we can't push that there. Ooh, let's... So let's push none. Okay. And then this is going to become a vector of optional type kinds. So if it's none, we haven't erased it yet. And if it's some, we have. So that's broken everything. Because this. So we match self erasures clone get unwrap. So now we know always there is going to be a value for the index, because every time we increment that index, we put an element in the array and we never clear the array. So now it's unhappy about this. Unexpected option. Yeah, so some. Does insert replace or does it throw? Shifting all elements after it. Okay. So there should be replace or set. Put. How do I replace? I guess you just have to do self erasures index equals. Yeah, I was overthinking it. Okay, so that, and then so here we want to force unwrap. Good. And then down here we want to force unwrap, and then this instead of insert is index equals some op in, and then this is unwrapped, and this is unwrapped. See how many times we clone the erasures? Yeah, all of this code is not correct, but hopefully that's worked. It has. So, okay. Let me. Okay, this is a case where reporting where the type was pushed isn't very good. So let's replace this with the OP span. So you can see what operation pushed that onto the stack. Oh, hang on. Yeah, this has gone very wrong. Shit. I knew this was going to be a pain. I knew that doing generics with these functions, inferring their type was going to be a real pain. Okay. So where are we creating all of these generics? So when we dupe, we're creating a generic, and when we map, we're creating a generic. So, I think I need to make another break and have a think about this, because I don't want this to just be me staring at this code the whole video. So I'll come back when I have some progress. Okay, I think I have something, and I wanted to keep recording to see if it would fix it, and if it doesn't, I'll just get rid of this chunk of the recording, but if it does, then it worked. So I noticed that it actually is working. So it's expecting a function of one generic to another, but it's getting a function of int to int. And that's because this expect type is just comparing two function types. It isn't actually comparing their arguments. So we need to, in expect type, see, are they both blocks? And if they are, we might have to do a little bit more erasure. There we go, that's a little bit more manageable, so let's get rid of that. So, we need to so we need to, first of all, if actual ins len equals expected len doesn't or come on Copilot, you got this, actual outs, okay, I'll do it myself, lens, there we go, actual outputs lens, yeah, we report an error which is basically the same as this, yeah, otherwise we to do it. So this should to do because it, yep. So this works. If instead I say this is, you know, function of int to int, oh, because it doesn't return after this. So actually, yeah, if I get rid of that to do, yeah. Expected 1 to 2, but got int to int. Okay, good. Yeah. Ooh, hello. Yeah, okay, so it type checked it. It type checked it in the sense that it didn't throw, or it didn't report a diagnostic, but we aren't done yet. So we basically need to say, okay, for actual it. Yeah, so we do need to zip. And then we just recursively call expect type. Okay, get some room. So self expect type. Oh wait, hang on. Is this? Yeah. Oh, it's a mutable call. So it might complain. It seems fine. But you're zipping the wrong things together, Copilot. Fuck's sake. Okay, so actual ins and expected ins. Expected in. And this is expected ins. You gotta be really careful. Like, it's so convenient having it just do these long lines, but you need to be careful that it's actually the right thing. And so sometimes you spend more time checking the code than you would have spent just writing it yourself. So we want the actual out and the expected out from the actual outs and the expected outs. And then we just do this. This is not going to work, I think. This is not going to work. Yep. Do you know why? Because we need to do a little bit of erasure in expect type. So this might actually be how we do erasure properly in expect type. So matching it actual and expected. If we, so which one is which? Which one is which? So the expected is the generic. I guess it doesn't really matter. We need to handle both cases. But if we have generic, yeah, and oh, this is the expected. Expected is on the right. Yeah. Well, to do that, if instead the generic is the expected, and we have a concrete actual. So this should be the one that we hit. Yep. Okay. So we want to match on the self erasures. Clone. Do we still need to? Yeah, we probably still need to clone, but get index. I think I've been doing this for too long. Yeah, match self erasures, get index. Which is the use size. Oh, because it's that, and then non-exhaustive patterns. Okay, it doesn't seem mad about me not cloning that. So if there's nothing, then we... If there's nothing, then we need to erase it. So we insert index actual clone. Yeah. If there is something in the expected, then we just say self expect type, and actual is actual, expected is the type kind, and the span is the span. Yeah, okay. There we go. We do need to clone. That's why. Okay. Does that work? Okay. Right. So we only have an int array left on the stack, or an int list left on the stack, because map popped off the function and it popped off the list, transformed the list, but using the erasures, it knows that it's a list of integers. So if I print this, we're going to get an interpreter error. I didn't need to rebuild it because that was just a change to the do program. We're going to get an interpreter error because we haven't implemented map yet. Okay, we're into the fun stuff now. This is easy. This is really easy because we just say if let value block ops equal self pop unwrap, because we know that there is a block there because we type check, so we will say else unreachable just in case we ever mess up. And then if let value list values equals not the ops, the next pop, else this is unreachable. We just have to construct a new list by transforming every value by the ops. So we need a sub-interpreter. We need a sub-interpreter because we don't want to pollute our interpreter's stack. So we want sub-interpreter equals a new interpreter. And we want to, for value in values, sub-interpreter stack push the value. Clone it. I don't even care. Yeah, it makes sense you have to clone it because otherwise, yeah, you need to clone it. So we push the value, and then for op in ops, sub-interpreter interpret. In fact, we don't even have to loop because we loop in the sub-interpreter. So sub-interpreter interpret ops. Do we need to clone those? No, because it takes them by borrowing them. Cool. And then once it's done that, yeah, so we've finished looping and we've interpreted those ops. What is left in the stack of that sub-interpreter is our next list. So we say self stack push exactly that, Copilot, exactly that. So if everything has gone well, this program here is going to map this list with this function, correctly type checking it as well, creating a list of ints that is the square of all of these. It's just that easy. It is just that easy. And that's not all. We could do a filter. We can try and implement filter. So we've got that. So let's do the same list, and let's just make sure there's no funky stuff. Yep, we can do that twice. The stack is fine. The stack isn't getting polluted. And instead, well, okay, let's instead say 3 greater than equal. Okay. Okay, that's the wrong way around that I would have expected. So something's up. I think maybe because let's see, you push the 1, you push the 3. So 3 greater than equal 1. Yeah, that's correct. Because if I was to say 1, 3 greater than equal print, it's true. Okay. But if I filter, what do I have instead? So let's go. In fact, let's just let's commit what we have. So let's do a quick cargo funt and a cargo clippy, and it is yeah, we haven't implemented that case. That could bite us later. Other than that, though, all good. So we'll commit that. So implement map. Good. So let's implement the filter keyword. And hopefully this is going to be smooth sailing, because we've done all the hard work of type checking already. So if we say filter, that is a filter keyword. Parser, that's going to be filter keyword to op kind of filter, so we need to add that. I should probably put filter above map because the alphabet. So let me just fix that. Cool. And then yeah, filter goes above here. So we need to type check filter, but this is going to be quite easy actually, because what we need to do, so if we copy map, we need a block that takes let's see, it takes a generic and it returns a bool. And this is filter. And it, yeah. That doesn't seem right, does it? Map should take both. Okay, I see why it worked. So this is technically wrong, but because it was the same type, although it worked with the Boolean array, so I'm not sure. Oh, I guess it worked because I was consuming it. So this also needs to say after the block, it takes a type kind list of generic A, which means we're going to need to clone A. Why isn't it like that? Okay, I have to put it in a box. Okay, it likes that. And we have to say it actually returns a list of generic B. And then the same for filter, because this is going to take a list of the A's, but it returns a list of bools? No. It still returns a list of A. It still returns a list of A. Because... Wait, do I even need to clone? No, because these are ints. It's been a long coding session. So it still returns an A. It's just a potentially a shorter array of A's, a shorter list of A's. Cool. So then we just implement it, I guess. So we basically start the same way, and we interpret, but we know that the result of this interpretation is a Boolean. So what do? We need to save the value. Okay, this one... Okay, no, we don't. We don't. So, once we've done this, we're going to have an array of Booleans, and we just need to iterate that array. So for value, well, I don't want to call it value, for result in subinterpreter stack. Hello, can I have a closing bracket, please? If let value bool, yeah, we'll call it result, and we can just shadow it because we don't need this again. Else unreachable. Again, can I have a closing bracket, please? Good lord. Else unreachable. So we know that this has a result. So then we say, okay, if result. Well, it really doesn't want to give me the closing bracket. Is there like some mismatch? Yeah, there's a mismatch one down here. That's why. So if the result was true, so rather than always pushing the stack, so if I do this, we instead want to keep our own results. If result, okay, we need to have the index as well. Stack enumerate, iterenumerate. If result, results push values I clone, and then we just return a list of the results. So that's horrible. That is absolutely disgusting, but it will work, I hope. Unused variable. Yep. We know that. We don't care what Clippy has to say. Expected 1 but got int. Oh, is this because of what I did to the type checker? Is there something wrong with me saying about the output types. If I get rid of that, and I get rid of this, because this shouldn't have worked. This shouldn't have worked, but it did. Also, yeah, we're not even filtering, we're just mapping. Helps if I rebuild. Yeah. So instead if I say 3 greater than filter, okay, so that's the elements for which 3 is greater than them. So that works. I don't understand why this. Okay, that's a little worrying. We'll have to look into that, why this is working without those and it didn't work with them. But okay. Okay, whatever. So we can filter. We can filter. So we can say square these and give me everything that is greater than, or everything that 10 is less than. Incredible stuff. So this is kind of working now. There's some gremlins in the type checking code. I'm not gonna say that this is correct, and there's a lot of instances of us erasing generics all over the place, and I wonder now if because it's done in the expect type method, wherever that's gone, here we do the erasure here. I wonder if you can remove a lot of the erasure code from elsewhere, because it's kind of, you just need to call expect type, and if one of them's a generic and the other one's not, then it should just work. But anyway, this has been a really long session, it feels like. But look, this is kind of what I wanted out of this language, is you have lists, you can quote functions, and then you can apply them. And in fact, you can do something stupid like this. At least I hope you can. So this is going to push the function, push the list, swap them, and then it should carry on as normal from there. So if I run that, yeah, absolutely. And if I do this and swap filter, it's still the same, because we push the predicate, we push the function, we push the list, so we swap the list and the function, and then we map as normal, and so we just have the list of the square numbers, and then we swap the predicate and that list of square numbers, we do the filtering, and then we print. Can your Porth do that? I don't think so. I don't think so. So, there's definitely something very wrong down here. There is something not right. So, to do, figure out why this works without having the lists in the ins and outs. But I think that's pretty good for a session. So let's actually go to the to-do, and let's see if we can tick anything off. So diagnostics, I'd say we've got pretty good diagnostics now. We still need some more stuff around having additional reporting locations of like, oh, you expected an int here, but you got a bool that was introduced here, sort of thing. We absolutely have lists. We absolutely have functions. So the next thing would be the REPL. So the REPL is going to be very interesting, because I imagine what you're going to do is you're just going to have like a terminal that you can type complete operations into. So a complete function or a complete list, or just a map or a dupe or a pop or something like that, and it will lex it, parse it, and then it will maintain a type stack in memory, and it will type check on that type stack, and then it will interpret it on another stack, and just sort of like loop that. So you can push things and map them and all that very reactively. And I think it would be really nice as well if there could be like a command or an operation or an operator rather, which just like prints the state of the stack. I think that would be really useful for the REPL. So as you're going, you can be like, okay, well, what actually is on the stack? And it will show you, oh, you have like a list of ints and so on. So I think that'd be really cool. But I think I have done a lot today, and I'm going to leave it there. So again, if you've enjoyed, and you've been along this journey with me, and you've probably been screaming at this code, and you probably know what's wrong with it, but yeah, drop a comment, drop a like, let me know what you like, what you didn't like, subscribe, all that stuff, I don't know. And yeah, I'll see you next time when we implement the REPL. So, bye-bye.